Okay, so we're going to do the math today. And so, yeah, let's go ahead and get started with that. Keys over here. So, with this, like, do either of you know like what the general formula it is? Which I guess has deltas in it, which are hard to type, but the general formula that we're going to be using for all of these, actually I'll go ahead and put it up here, is going to be delta G, let's do delta. Okay, it's going to be delta G is equal to delta H minus delta, or minus T delta S. And delta, and really I think all of these should have the little knots in the them too, but it's not too important for just practicing this. So we're going to do that for this because we need to figure out whether each are spontaneous, and how you know if a reaction is or isn't spontaneous is based on delta G. So we're going to go ahead and solve for this. So we got the equation we're using. Put in here. Oh, that's not what we want. It's not going to work right. Okay. Okay, so we're going to use that. I'll put it over here. So we don't know delta G obviously yet, but what we do know is that, oh, I have the whole thing. We do know these other numbers that they gave us. So we can go ahead and plug everything in. But there is one problem, because if you look at it, you notice that we have this one in kilojoules and this one in joules per Kelvin. So those are going to have to be moved around so that that's not how it is. And so we need to, I'm going to just choose that we turn this one into kilojoules. So to turn this one into kilojoules, I have to, move our decimal over 3 times. So then we end up with 0.3 or 13138 kilojoules per Kelvin. So now we have everything in the same units, so that'll work now. So we're going to have our, first we have our negative 75.9 kilojoules for H. We can plug that in. And then we're going to have minus the temperature, so 273 Kelvin, times times the delta S, so 138 kilojoules per Kelvin. So if you go ahead and solve that, what do you come up with? Oh, I forgot to open my chat. Let me open that so I can see what you guys are sending in. And just like before, you can send in the chat to answer things or ask questions, or you can unmute yourself and talk at any time. That's fine too. So I left out the decimal here. Don't do that when you're solving it. That's not going to do you much good. That's not quite what I came up with. Cool, cool. Yeah, we got your calculator. We're going to use it less today. So and that could have had to do with, yep, perfect. Perfect. Except for it's negative. So yeah, second one there. Perfect there. Or last one. Perfect. So we're going to have our delta G is equal to, should write that here, negative 113. No, that's not right. 113. We'll go ahead and leave it at three places. So I guess that rounds up. So it's negative 114. Okay. And that's going to be, in our units, is going to be kilojoules. And so looking at this, is this going to be spontaneous or non-spontaneous? It's based off of one thing, and that is this right here. So this one's going to be spontaneous because it is releasing the Gibbs free energy. So it's negative. It's releasing it, so that means it's spontaneous. So now we're going to come over here to our next one. Same equation as before, because we have the same information and we're trying to find the same thing. So this will be a chance for you guys to practice this again. So we have delta H. So just like before, we're going to go and plug it in. So we have delta H is negative 27.3 kilojoules. Oh, and just like before, we're going to have to go move this back into kilojoules too. So that's going to be equal to negative 0.0552 kilojoules per Kelvin. And so then we can go ahead and plug in the rest of this. So this is minus T, so 535 Kelvin times negative 0.0552 kilojoules per Kelvin. So we have that. So if you guys solve that, what do you come up with? That's not quite what I had. Let me go ahead and put it in my calculator again in case I messed something up whenever I figured this out before. No, that's not quite what I came up with. I got the same thing I did before. Wonder if this might make a difference. Yes, perfect. 2.2 is right. I think, okay, so I look back at it, I think the mistake that you guys made is you left out this negative right here, which is kind of small. Can you guys see those very well? I can probably make this a little bit bigger. That's helpful. But we're only at 90%. That definitely would help. There we go. But yeah, if you, that negative right there, I think is what made that difference. So delta G is equal to 2.23. See, you said you're having errors with your calculator. Do you have one of the calculators where you type it exactly like you see it? Okay, yeah, I think so. Maybe try putting a parentheses around that and make sure if it has a difference between a negative and a minus sign, because a lot of them do. That could be the issue, is if you're putting a negative or putting a minus instead of a negative like here. That could make the difference. Try it again and see if that helps. And if it doesn't, you might Google it and see what you come up with. I'm not that familiar with that kind of calculator. Okay. Go ahead and get this next one. Okay, well, good luck. If you still have issues and can't figure it out before like our next session, let me know and I'll see if there's anything I can do to help you. Let's see. So this one, what numbers are we gonna plug in here? I guess we have the thing we have to do first. So we have to change this first. Perfect. Yep, that's perfect. And okay, so one thing, Alyssa, you may go ahead and put a parentheses around the outside of all of those. It shouldn't matter, but I would if it causes you any problems. You might try to put a parentheses around like you did. I don't know. I'm not sure. But yes, that is exactly right. Here, I'm actually going to just steal that so I don't type the whole thing again. And so if you do that, what do you come up with? Whoa, that's not what we wanted. Perfect. So we're going to go ahead and round the 442.8. We're going to round it to 443. Just leave it with the 3 sig figs, just like the rest of this. All right. So, oh yes, and I forgot about this part. So is B here, is this going to be spontaneous or non-spontaneous? Non-spontaneous, perfect. And that's because this is positive. Delta G is positive, it's non-spontaneous. If it's negative, it's spontaneous. So that's going to make this one, because it's also positive, also non-spontaneous. So if the reaction quotient Q is less than the equilibrium constant K, what is true about the Gibbs free energy? So what it's saying here is when Q is greater than K, delta G is negative. I think we might have had this on our last one. I think I might have repeated this. I apologize if I did. Which means that it is spontaneous. Delta G is negative, then it's spontaneous. And just like we were talking about here, if delta G is positive, it's not spontaneous. What does it mean to be thermodynamically favorable? At least we can do that. You can still see that if you need it. So if it's thermodynamically favorable, then it's going to be spontaneous, is what that means. So we put a spontaneous reaction is thermodynamically favorable. And that's what makes it spontaneous, is it's favorable to occur. If it's not favorable to occur, then it's going to be spontaneous. What does entropically favorable mean? Entropically favorable, that's probably how you pronounce that. What does entropically favorable mean? So either the products or the reactants are going to have more entropy. Which one has to have more for it to be entropically favorable? No, it's not going to be non-spontaneous, not for this. So you think if the products or the reactants have more entropy, it makes it favorable? Just throw a guess out there. Y'all can do it. Reactants? It's actually when the products have more, because entropy is basically disorder. So if it's going to have more disorder in the products, and then it's going to be entropically favorable. So it's when the products have more entropy than the reactant. So yeah, because like we talked about before, entropy is disorder. and things, I guess, tend to move toward disorder is how we count that. Suppose that a reaction has delta H equals negative 28 kilojoules and delta S equals 60 joules per Kelvin. At what temperature will it change from spontaneous to non-spontaneous? There it is. Looking at my key here. Okay, so we're using the same equation that we did before. If you look at it, you kind of have the same information, except that you know this time that you're trying to find this point here where it's at equilibrium right between the spontaneous, non-spontaneous there. So need this equation, and I'm just going to copy and paste it again because then I don't have to go find delta. Here it is. So we have our equation, and what do we know? We know that, it's a side note over here, we know that at equilibrium, delta G equals what? Equals K, no, Q equals K at equilibrium, not delta G. Close, close. Delta G actually equals 0 at equilibrium. So if you remember, if it's negative, it's spontaneous. If it's positive, it's not spontaneous. So we're trying to find that in between here. So that's why we decided that. So we're looking at that. So therefore, we know that this is what we're trying to find, is if G is 0. So we can go ahead and plug that in. So we have 0 equals what? So they gave us delta H and delta S, and once more we have kilojoules and we have joules. So we'll go ahead and change this one here. So we'll have negative 28 kilojoules minus, and that's going to be T, which we don't know, times the delta S. So we're going to have our point here. So we have our negative 0.060 kilojoules per Kelvin. And so then we can go ahead and move these around and solve. And if you want to, you can move them, like, you can move it here, move them around here, or you can wait and move them around here and move them one thing at a time. Either one is up to you. I usually prefer to go ahead and move them around at this point and just move the symbols around, but honestly, any of it's fine. So if I was going to do that method, then I would have went ahead and changed this to that equation out there. So I would have went ahead and moved this around and gone, okay, so we're gonna we're trying to get T by itself. So I would have moved like delta H over to the other side. So it would have ended up being negative over on this side. And then this whole thing would have been negative. So we need to get rid of that negative and this. So this would have been divided by negative delta S over here. Go ahead and put parentheses. So if we divide both sides by negative delta S, then you can find it that way too. So, and then also if you want to, just to get rid of some of your negatives, you could like, yeah, you could like make this like negative and this positive and this negative, like just flip the signs of all of them if you want, but either way is fine. So then if you do it that way, you end up with, at this point, delta G, so 0 minus delta H, which is your negative 28 kilojoules, minus your delta H, oh, never mind, that was delta H, sorry, divided by negative delta S. So our negatives are going to cancel out, and we're just going to end up with our 0.060 kilojoules per Kelvin. And so I prefer to do it that way, because then you have this whole thing is T, so that you don't have to like go around moving everything. So that is just helpful for me. I don't know, you can do it however you prefer. Why don't you go ahead and solve this and see what you come up with for T. And you can solve it either way. I get that, except I think I just rounded something in there different. I got 467 Kelvin. And so that's literally like if you keep everything else constant and you just like change the temperature and that's it, this is the point at which it changes. So anything, which way would it be? So if you have a higher temperature, I believe, no. Actually, if you have a lower temperature, since it's multiplying by negative, that ended up being positive. It's going to make it higher there. So, I don't know, but yeah, look at that. So, on to the next one. If the following equation is at equilibrium, what is T? So, look at this. So what we know is that we have our products, reactants over here on this side, and we have our products over here, So, and we know that we have, so that means that these are our initial values of things and these are our final values. And we're trying to do, we're trying to do the same thing we did here, except for we don't know we don't know our delta H and delta S values. We have to find them ourselves. So we have to do. So, where are we at? So we're using the same equation. And so we're trying to find temperature at equilibrium. So we know we're solving for T again, so we can go ahead and use this. You don't have to move everything around all over again. I'm going to put T in the beginning, just because I can. So we need to find delta G. And we talked about that up here. Oh no, we didn't talk about which one was which, actually. I think we talked about another one. I don't want to mix those up on you guys. Yeah, so delta, this one. So these ones are going to be your just so we don't mix them up, our S values. And these ones up here are going to be our G values. Or not G values, our H values. Apologize. Enthalpy is H, as in heat, and then entropy is S. So I don't know if that helps you remember, but and here we go. So we're gonna have to find these. So let's go ahead and find delta H first. So delta H is going to be, it's going to be equal to delta H final minus delta H initial. I can make that small, I think. Let's see. Minus the delta H initial. So products minus reactants, just like before. So what is that going to be? So we're going to have that is equal to, and we're going to go ahead and be able to solve from this. So like we talked about, here's our H values here. So enthalpy is H. So we're going to go ahead and plug those values in, and we'll have our negative 241.8 kilojoules minus our negative 285.9 kilojoules. Oops. And that is going to be equal to what? No, wait. Oh, I left the negative off mine when I solved it. Okay. Yes, except it's going to be not negative 44.1, but positive. And that makes sense if you look at it, because you know these signs are going to cancel out, and that's going to end up being a plus sign. And so you're going to have, this is a bigger number than that, so you're going to have more positive than negative here. Yeah. So you're exactly right, except for flip your sign. So it's going to be, we'll go ahead and keep our 4 sig figs there too. So we go, actually no, addition subtraction, so we just keep our 1 decimal. So yeah, 44.1, that's right. And that's going to be kilojoules. Okay, so now let's go ahead and find our delta S. So we need this one here. So delta S, you're going to solve it exactly the same way. So we're going to have our delta S final minus our delta S, or not delta. These don't need to be delta. I apologize. That's just H and S. S final minus S initial, because this is what doing final minus initial is what makes it delta. So we're going to have, just like before, do our, oh, but we're going to have to go ahead and change these into kilojoules again. Yes, change it to kilojoules every time if they have the kilojoules and the joules. Unless you like ask for the unit and specific answer, then if you ask for joules, you can change the other one to make it. But yeah, we'll go ahead and change this into kilojoules. So I think I can do this here. Yeah. So that's going to be equal to 0.0699 kilojoules per Kelvin. And there we go. And this one is going to be equal to 0.188 kilojoules per Kelvin. Okay, so you can go ahead and plug your numbers in here and have your 0.188 kilojoules per Kelvin. And then you're going to have that one minus the other one, so 0.0699 kilojoules per Kelvin. And when you solve that, let me know what you come up with. Yes, that's perfect. We're going to have the going to be 0.118, and so what we had 3 decimal places, so we'll keep 3. So then next we just have to go plug these values in. These are our important numbers we've come up with here. That one, this one. So we're going to go plug those in. So we're going to have T equals delta G, which we know is 0 because we're finding it at equilibrium, minus delta H, so this value here, 44.1 kilojoules. And then, then we're going to subtract our, oh no, we're not subtracting. I did the same thing I did earlier, apologize guys. Divided by our negative delta S here. So we're going to have 0.118. And we're going to solve that. And let me know what you come up with. $373.7. Perfect. And so we're just going to go ahead and keep just what's it called? Just 3 sig figs there. And so it's going to be 373 or not 373, 374 kilojoules, or not kilojoules, Kelvin. And I forgot to write my unit on this one and that one. So this is the kilojoules per Kelvin. And that's what we're putting here too, kilojoules per Kelvin. And here's our answer. So that's equilibrium at T, or that's T at equilibrium, said that backwards. So yeah, that's what we came up with for today. Do you guys have any questions or anything like that I can help you with from this or any of your other stuff? And then also I want to remind you guys that you have an exam coming up next Tuesday, so just a little over a week. And so don't fall behind on things. Yes, we will do a test review. I'm not exactly sure when yet, but we will have one before your exam. And if you guys have anything that like you're struggling with and you want to cover, you can send that to me on here. You can send that to me on Remind, and I can make sure we include that in our prep. So yeah, that's all I have for you guys today. So let me know if you have any questions. Aside from that, I think we are done.